Okay, we're recording. All right, so next week is your big assignment, big poster presentation. And as I mentioned many times, it's different this year, and so we don't really know what it's going to look like. We hope it'll work well, but you never know. Things might go awry. So far, it looks like it's going to go without a hitch. It looks that way, but you never know. You never know. A few points to know. First of all, it's happening Friday and Saturday. You will know when your night is. We're developing the schedule right now. We'll have it ready by Monday. It'll be on the website by Tuesday, so you'll know whether you're scheduled to present either Friday night or Saturday morning. Okay? And you're welcome to come for the entire thing and watch other people. Every time. Every single time. Does anyone know? Like, what is it? Every single time. All right. So, we want you to show up in photo next Friday night or Saturday morning, or both. Right? So, where are you going to go? You're going to go to photo 135. That is where our headquarters will be for the evening. Show up there with your team and register so we know that you are present. And you will be told then which room to go to. You know already which room to go to, but go there to tell us anyway. The actual presentations will take place in these rooms. Dr. Gomez's class has claimed this one and that one, I believe, so you will probably be in one of these two rooms. But you'll know from the schedule that will be posted on Tuesday. What is required of you? Okay, like I said, we're going to post a schedule soon, so you'll know when you are scheduled. You won't know who your judges are. We will know. You'll know when you walk in the door. Surprise, hey, it's whatever, right? Your judges will be a selection of graduate students, professors, and scientists from the community, probably 2 or 3 at a time. You will present one time and one time only. In the past, you presented twice. This time, one time only. But the judges will question you for that one time, and they will each give an assessment of your performance, and we'll take the average mark. Okay, so show up at least half an hour before you are scheduled. Probably everyone will show up at 5, I assume, because you'll all be terrified, which is a wise thing to do. But if not, make sure at least half an hour. Why? Because we want to make sure that you're there. We have to make sure we have your presentation so we can upload it. I want you as well to email me an electronic version of your poster a day before. I'm not marking that. That's fine. It's just to make sure we have it just in case you forget to bring it. We can have it upload ready to go. As well, bring it on a USB key so that we can make sure we upload. So in case you've made any changes in the last second, this is your opportunity to do so. Okay, when you email it to me, put in the subject line which class you're in, A or B. This is B. A is Gomez's class. And the surnames of your members so we can access it quickly and upload it on the day of the event. Like I said, you are welcome to attend other people's presentations. That means if you're the first person up, you're screwed. You're the test presentation for everybody else to watch. But that's nature of the draw, right? But you're welcome to watch. You cannot ask questions, though. Do not make your fellow students extra anxious by bugging them with more questions. The judges will ask plenty of questions as it is. There'll be somebody in the so the way it's set up, it'll be a big classroom, right? The judges will be there. You'll be standing up here. We'll project the poster over here. Everyone will present. The judges will ask questions. There'll be a timer. So one of our volunteers would be there to make sure that you're on time and to progress to the next presentation and so forth and to collect the judges' decisions. Yes? Does every student have to? Yes. We'll get to that stuff. No. I see where this is going. So apparently only one person knows what they're talking about. All right. I see where this is going. So for your presentation, dress well. Not like this. Pretend you're at a real conference. In the past, we've actually made it a real conference, so it was kind of fun to get dressed up. It's actually one of the fun observations over 8 years of doing this is seeing the evolution of conference fashion. When I first started doing this, people dressed as if they're going out clubbing. Right? Like, that's not a miniskirt, that's a belt, right? And now it's actual suits and stuff, which is a fascinating evolution. All members of your group must speak. So in the presentation phase, we will notice if someone is silent. In the Q&A, not necessarily, right? It doesn't matter. So your presentation can be a maximum of 10 minutes. Again, there'll be a timer there to stop you. And prepare to answer about 5 minutes worth of questions. The judges may go over time a few minutes. They have that leeway. So your poster is a single slide. This is not a click-through presentation. It's a single slide that ideally would have been printed into a 4-foot by 4-foot thing that you stick onto a board, but we're saving you the expense of doing that by having you project a single slide with all your information on it. So pretend it's physical and post it onto the wall. Right? So that's, you'll be standing here next to it. Obviously, you don't stand in front of it. That'll block it. The judges may go up and look at it very quickly, may stand around you as you present, so they get a better look at it. Okay, other stuff. We will have refreshments for you, so coffee in 135 to get thoroughly coked up and anxious. We also will have a podcaster present. Did I say coked? I mean Pepsi'd up and anxious. We'll have students recording a podcast too, so you may be asked to do an interview. Recognize that if you give your consent to be interviewed, we will accept that as consent to have your interview broadcast on the national podcast. So we have a couple of people who will be doing that. We'll have a situation set up in the corner. You may be invited over to talk about your research or whatever. Or maybe not. Maybe they don't want to talk to you. Who knows? But I'll be surprised. As well, as I mentioned, your abstract will be published. All right, fine. Whoa. Happens every time. Two things happen every class. The battery goes dead and someone leaves in the first 5 minutes. It's amazing. Okay, so we're publishing the abstract. This year we will not be printing out physical copies of the booklet to save money, but it will be in PDF form and probably on Amazon as well to give it a semblance of authoritativeness. So you can access it probably on the day of the event, and you can cite that on your CV. And I'll be posting instructions of how to cite it on your CV on the official CSEBU Ottawa website. That's all the stuff about the poster day. Questions? Yeah. So if we are on Saturday, can we do that on the Friday? Sure. I mean, ideally I want on a Thursday, but if I'm not marking that. So if you can't get it in, you can't get it in. It's just there to make sure we have a backup in case you forget to bring it. If you haven't got that and you didn't bring it, then you're out of luck, right? So it's for your own benefit to send me something. So I won't be keeping track of who has and who hasn't. Okay. Any other questions? Here's a chance. Yes, sir. Yeah, it's on the website already. People who don't pay attention. It's called the Rubric. Other questions? Okay, I'll tell you a story. When I first did this, before I was a professor here, I was brought in as a judge, and I made the students cry. And I was shocked by this. And ever since then, I want to see tears every year. Right, that's my goal. So, and the way I made them cry, not intending to, was you asked them to define a word that they used on their poster. So know what the words mean, right? And the judges will be, my judges will be instructed in a certain way different from Gomez's judges. We have that leeway. So I will tell my judges to look for rigor. Rigor in the phrasing of the research question. Rigor in how well you phrased or thought through your search process for finding the papers. Rigor in did you have an assessment process for assessing of the quality of the papers that you found. Have you expressed the results, meaning the papers that you found and the information taken from it? Have you synthesized a finding and answered your research question? You are not responsible for what you find. Right? That's the responsibility of scientists around the world who publish these papers. You're responsible for your phrasing of the question and your answering of the question and the process by which you went about answering the question. So this is all about rigor and systematic thinking. No one expects you to be an expert on this. Right? If your topic is butt cancer and ballpoint pens, I don't know. If they ask, what are ballpoint pens made of? Well, you don't have to know. It's a 2-week exercise. We don't expect you to have Nobel Prize-winning science. We expect you to have a logical thought process through which you can defend the decisions that you made in this endeavor. Don't defend what the scientists did, like, hey, they did this case control study when clearly it should be a cohort. That's not your fault. Right? But defend, we chose to limit our search parameters to things published in Polish. Why? There's got to be a reason for that. Or things published since 1995. Why? There's got to be a reason for that. So be prepared to answer those kinds of questions about decisions that you made and also about the insights that you may have gleaned through the process. What should we do about your findings? What should policymakers do? What will be the next step in research? If you had to do this all over again with $1 billion, what would you have done differently, etc. Cool? I'll be having special office hours on Thursday to answer any last-minute issues. So there's always that. And because I won't be having a regular lecture before the final exam, I'll be setting up, again, special office hours in the following week, extended, to come in and talk about other outstanding issues before the final exam. And I'll be uploading either a document and or a video describing the final exam. But until then, about the final exam, it will be multiple choice, because it's health sciences, that's what we do. You will have a cheat sheet, double-sided with anything you want on it, and it is cumulative, meaning anything goes. Any questions about the exam before I move on? Yes, sir? No, I don't think so, no. To be honest, it's easier to think of exam questions that have to do with the first half of the class. That doesn't mean it's that way weighted. It just means if I'm lazy, I'm going to think, oh, here's some incidence and prevalence questions. But I will try to make it as balanced as possible. Yes, sir? From the first midterm itself? Why would I tell you that? Well, question 6 on the back of the book, no, I'm going to tell you, it might be. That's how lazy I am. I know what'll happen. People will want to, I got to see my midterm now, especially office, I see a midterm. If I tell you yes, then there'll be a line up at the TA's office wanting to see the midterm. If I say no, then there won't be. So I'm going to tell you no. Any other questions? God, this class. All right, moving on. We have 2 topics to cover today. You'll notice in the syllabus last week we had this thing called decision analysis. I've decided to take that out of the syllabus. So one fewer topic we're going to cover. Decision analysis is not core epidemiology. It's a little thing I throw in some years that's kind of fun. It's using statistical techniques to make clinical decisions. This late in the game, it can be confusing for people, so I'm going to leave that out entirely. So don't worry about that because it's in the syllabus. But first, we're going to do some stats review. If you remember from second year stats, hopefully you had a professor who covered a little bit of sample size calculation. And the reason this is important is poweredness is an important consideration for whether or not a study is good. If it's underpowered, then it is invalid. We cannot make generalizations about the grander population. It's possible to be overpowered as well. Underpowered meaning has not enough people in the study. Overpowered meaning having too many people in the study. How does that work? Let me tell you a story. Well, let me tell you a story, kids. Gather around. So every year, CMAJ, the Canadian Medical Association Journal, has their Christmas edition is a little jokey. It has real science, but not very useful science. And many years ago, a paper they published was on, is there an association between your astrological symbol and whether or not you have a higher chance of winning a Nobel Prize in medicine? Turns out that you have a higher chance of winning a Nobel Prize if you're a Gemini, I think it is. Yeah, usually every year someone says, woo, I'm a Gemini. Okay, so you can conclude a couple things from this. One, that, hey, that's great. It means there's something real about astrology. Or you can conclude that with a large enough sample size, you can prove anything. And that's really what's happening there. If a large enough sample size, you're going to find spurious associations that may be internally valid, but not externally valid. So I'm off on a tangent there. But so when we talk about sample size and poweredness, both extremes can be problematic. So the slides I'm going to present to you were developed by my good friend Nick Berriman, who is a statistician at CHIO. He's the guy who wrote that paper with BMJ about placebo effect. And he gave a guest lecture in this class many years ago, and I just stole his slides, and I gave the same lecture. So we're going to talk about an example of using a drug to lower blood pressure. We're going to go over what the Null Hypothesis means, type 1 and type 2 error, what the sampling distribution means, and finally we're going to look at 2 formulas for computing sample size for a single group study and a 2-group study. And if you had me in second year stats, this will be a review. If not, this will be relatively new. Okay, the example. The example we're going to work through is some doctors are designing a study to test whether or not a new drug lowers blood pressure in patients with high blood pressure. Does it work? Well, we're going to have a study. Okay? How many people do we need in the study to give us confidence that, in fact, this drug works? Because it's one thing to say it works in my friends, but can that be generalized to a larger population? Can we infer that the internally valid conclusions in my sample are externally valid to the larger population? If we have too few people, we won't be able to detect an effect, even if there is one. And if there are too many, we will expose patients to risk, but also may find spurious associations. But in general, this is the bigger risk. Right? We have to keep our numbers down, not to have too many people at risk, and also to keep the cost down, because these are expensive ordeals. Okay, what's a null hypothesis? If you remember your second-year stats, you know that a null hypothesis is the baseline conservative assumption of what's going on. And we always assume at baseline that nothing's going on. It's like in a court of law, we always assume that the person on trial is not guilty. And the trial is the test or the study that determines whether or not we can throw out that assumption and see, you know what, there's sufficient evidence that we can reject this assumption that he's not guilty and assume that he is guilty. With sufficient evidence in an experiment or a study, we develop evidence so we can throw out the null hypothesis that nothing's going on and say, something's going on. So, for this kind of study, the null hypothesis would be the intervention is associated with no reduction in blood pressure, meaning that the drug does not work. That's what we're trying to reject. Okay, so H sub naught is usually our short form for writing down the null, right? And this is the burden of proof that we're trying to overcome. Innocent until proven guilty, doesn't work until we prove that it does, right? So we're going to design a study to put the null hypothesis to the test. So this table is useful for thinking about the kinds of errors that might occur as we test our drug. If you think about it as a courtroom scenario, think of it this way. This is what the jury is going to decide, and this is what reality is. So on the rows are going to be what the jury decides or what the test results are, and the columns are what reality is in both cases. So let's say the jury decides that the man is guilty, or the jury decides the man is not guilty. That's the same as saying the test says that has an effect and it doesn't have an effect. So we have four possibilities. First, we can say we accept the null, or we can reject the null. So accepting the null, we actually don't say that statistically. We usually say we fail to reject it. And the reason for that is O.J. Simpson goes on trial. We assume he's not guilty until proven that he's guilty. There was insufficient evidence to show that he was guilty, so O.J. Simpson did not go to jail. We all know he did it, right? So we can't say that he was proven innocent. What we can say is there is insufficient evidence to throw out the assumption that he's not guilty. But we never say, you know what, he's actually not guilty, he's actually innocent. So in the criminal justice system, we never say someone's innocent. We always say they're not guilty, because we don't know for sure. All we know is we did not meet that burden of proof. So the two possibilities here are we correctly said that nothing's going on, or we correctly said, something's going on. We have two kinds of error, a type 1 error and a type 2 error. The type 1 error is when we say the drug works, but it doesn't actually work. And a type 2 error says the drug doesn't work, but it actually does. So think about this in terms of a courtroom situation again. What's worse, setting a guilty man free, or sending an innocent man to prison? In general, our society likes to say that it is worse to send an innocent man to prison. So we set up our criminal justice system to really lower the chances of that happening. If that means that we heighten the chance of letting a guilty man go free, then so be it. That's the price we pay for making sure the innocent don't go to prison. Right? The innocent do go to prison occasionally, but the chances of that are small. The same happens here. So we want to lessen the chances that we will find a drug that we lessen the chances that a drug that doesn't work ends up in the market by heightening the chances that a drug that does work is not accepted by us. So that's between type 1 and type 2 error. Type 1 error is incorrectly rejecting the null, and type 2 error is incorrectly not rejecting the null. So keep that in mind. It'll come into play in a second. So here we're going to look at, try to infer the findings from our study for a larger population. That is the essence of most kinds of statistics. We call that inferential statistics. We do something with our sample and try to infer something about the grander population. So in this case, the grander population is people with high blood pressure, right? So we have the sample taken from all these people, right? And we are going to infer something about this population from our random sample. It has to be a random sample. Otherwise, these inferential techniques will not work. So consider now this. This is the distribution of the change in blood pressure in general. What does that mean? It means that if I were to take a random selection of people in general and see how much the blood pressure changes, and throw them back in the pot, take another random sample, see how much the blood pressure changes, another, and so forth, do it 1 billion times, and plotted the frequency of how many times different amounts of blood pressure change happen, I will always get this bell curve, this Gaussian distribution. That's the nature of something we call central tendency. It's a magical thing in statistics that allows all this to happen. And the width of that curve is a standard deviation. Now, a strange thing happens. The more sample I have, the more narrow that distribution becomes. So this is 1 person, 2, 5, 7. Right? When I say 1 person, I mean if I took 1 person out of a 1 billion and I measured how much their blood pressure changed, maybe it was like this much. Take another person, maybe it's this much. Another person. I take it, do this 1 billion times, the distribution of that 1 person sample looks like this. A 2-person sample looks like that. A 5-person sample looks like that. In other words, the width, the variation, the variability, the randomness of my sample, of the amount of blood pressure change I can expect, gets less the more sample I get. That means having more sample usually gives me a tighter estimate of how much blood pressure change I can expect. Okay? Increasing the sample size reduces the variability of this size. Okay? Now, we measure the error of this sample by taking the standard deviation and divide it by our total number of people in our sample. So you see there, as this gets bigger, the error gets smaller. So the more sample, the smaller the error. Fantastic. More people, better. That's a takeaway. Okay, now, when we do this kinds of testing, we have this thing called the null distribution. This is how much blood pressure will change assuming the drug doesn't work, assuming the null hypothesis is true. So let's say in our sample now, my sample of X numbers of people, I observe that my blood pressure changed by this amount. In this distribution, that looks like it's unusual. This is where the most usual amount of change happens. So a very small number of people have this change, a small number of people have that change. The question before us is this so unusual that it is extraordinary? If it's extraordinary, we can say, something big has happened here. If it's not extraordinary, we say, this is just same old nonsense. So we have to have a cutoff of where we decide that something is extraordinary. And that cutoff is where we decide statistical significance is. Okay? So we call that cutoff area the rejection region. And this is an arbitrary choice, more or less. Historically, we have some traditions that we apply to this, but never forget it's a relatively arbitrary choice how far along this cutoff is. So let's say we observe a blood pressure difference of like 20 millimeters of mercury. The average difference to observe if the drug doesn't work is like 5. Ours is 20. Is that so big that it's extraordinary? Well, if our cutoff is here, then yes, that we can say our change is significant. So over here, we say, it's still pretty close to the average, so it's not extraordinary. Nothing's happening here. Okay. We have this thing called two-sided test versus one-sided tests. What that means is, do we care if our blood pressure change is a lot bigger than the average or a lot smaller than the average? In general, we don't care. Usually we don't care. A one-tailed test says we do care. We care what direction is happening. A two-tailed test says we don't care. So most tests are by default two-tailed. Right? So our cutoff region, we care about, is it really extreme over here or really extreme over there? All right, so we'll get back to that in a second. But here's our rejection area. This amount here is actually how much type 1 error there is, how much type 1 error we're willing to accept. Again, the error of incorrectly rejecting the null. Okay? And we call that error alpha. So that amount of space there we call alpha. The thing is that sometimes we need to denote something called an alternative hypothesis. The alternative hypothesis is, let's say the drug works. If the drug works, what can I expect? So this first one here, this is the distribution of the blood pressure change if the drug doesn't work, and this one here is the distribution of blood pressure change if it does work. The difference between that is the amount of change we can detect. Right? So, and this red part here, that's our type 1 error. That's how much rejection we're going to take. The blue part is the type 2 error. In other words, the probability of incorrectly accepting the null. We want this to be very small. We're willing to accept a little more of this. So as I increase how much type 1 error I have less type 2 error. So there's a trade-off there. Okay. So what do I do now? Well, what we usually do is we fix the type 1 error. We say that's not going to move. And by tradition, we say it's about 5%. That's problematic. There's no reason for that. That's just history. History says 5%, so 0.05. Right? Some people say 0.01. Some people say 0.001. In real grown-up professional science, we actually don't have a cutoff. We just say, this is the number, you make up your own minds. Right? And so we try to fix it as something, and then we minimize the type 2 error. Okay? Power, this thing called power, that's defined as 1 minus the type 2 error. If all this is confusing, don't worry about it. Just remember the formula then. Okay? Power is 1 minus type 2 error. More power means that we are more likely to have the power to detect a significant difference. So watch what happens here. So here, remember last time, the more red we had, less blue. If our red can't change, what we can do now is move the effect size. So the difference between these two is how much difference we can detect. 10 millimeters of mercury, 50 millimeters of mercury, etc. If I'm willing to say, you know what, my threshold for detection is quite large, then I'm going to have a small type 1 error and a small type 2 error. If I'm going to say, you know what, I need to detect a very small difference, that means I'm going to have a small type 1 error but a big type 2 error. A very large chance of incorrectly accepting the null. So how do I account for this? I'm going to maximize power. I do this by increasing my numbers. When I increase my numbers, this happens. See? So now the difference between these two does not change, right? So I'm detecting the same amount, same difference, but the more people I add to my sample, I'm maintaining how much I can detect while minimizing both kinds of error. That's the takeaway from this. By increasing numbers, I can just keep my type 1 and type 2 errors as small as possible while maintaining the effect size that I can detect. Okay, so now let's try to compute some of this. Sample size calculations are very complicated, but I'm going to give you two very simple formulas that hold things constant. So to do this, we need to know the variance, the sigma squared, the standard deviation squared. And we're going to fix alpha, the type 1 error, at 0.05 for two-tailed tests. Right? And we're going to say that power is 80%. So 1 minus type 2 error is 80%. So the formula I give you only works in this scenario. That's very important. So in an exam question, I have to tell you that these are the conditions before the formula will work. The formula says only that alpha is 0.05 and power is 80%. And that's the formula. Okay? So you must know the variance. Delta is the difference again, the difference between those two curves, the amount of sensitivity that you want to detect, the difference between the control group and the experimental group blood pressure. the effect size. As you see, as delta increases, I need fewer people. As variance increases, I need more people. Now let's say the n that I compute is 10.1. How many people do I need? Do I need 10 or do I need 11? I can't have 10.1 people, right? Do I need 10 or 11? Yep. Why? Well, because 10 is less than the number that I need. Okay, so I'm underpowered. 11, I'm sufficiently powered. So the smallest number that is sufficiently powered is 11. 11 people, because it has to be an integer. That's the only takeaway. So this is for a single group study. So in other words, I'm looking at one group taking the drug and see how much the blood pressure changes. So example, standard deviation of the change is anticipated to be 7 millimeters of mercury. The variance is going to be the square of that, 49. How do I know that? If I'm doing the study, how do I know what the standard deviation is going to be? Where can I possibly find out this information? Who's got a creative research mind here that will serve them well next Friday? Apparently nobody. Interesting. So you get this from two ways. Oh, yes, back there? Previous studies. Exactly. Possibly a pilot study. Or from the literature. If there is no literature, then you do a pilot study. Or fake it. You have some estimate of this. Okay? And we're going to fix alpha at 0.05, and the power is going to be 80%. Great. And we're going to detect this. That's going to be our delta. That's how much stuff the difference we're going to detect, 5 millimeters of mercury. Right? So you plug in the numbers, this squared times 8 divided by that squared, and we get 16 people. Okay? What happens if there are two groups now? Do you double that? Nope. It's different. If there are two groups, we have a control group and an experimental group, right? So, same assumptions, but the formula is that. It's not 4 times sigma, it's 16 times sigma. Sorry, it's not 8 times, it's 16 times per group. So we have two groups now. Previously, it was 8 times sigma squared over delta squared for one group. Now it's 16 times for two groups. That means you have 4 times the number of people needed. Not twice the number, but 4 times the number of people. And once again, it's the n per group. So if I compute the n per group as 10.1, how many people do I need for a two-group study? Yes? No. $22. Right? I say this is 4 times what the previous one would have been. It's not 4 times what it is. So you plug in the numbers, I get 10.1, 10.1 per group. That means 11 per group, or 22 people. What some people do is they multiply by 2 and get 20.2 and round up to 21 for some weird reason. It's 22. Everyone see that? Yeah, good times. Okay, this is per group. Fantastic. Okay, so this is 4 times as large as the previous example, which is 4. Okay, so we want to carry patients from the control group to the placebo group. We have our standard deviation of 7, which means, again, our variance is 49. We have the same alpha situation, and we need 32, which is, okay, cool, right on. Okay. There are many ways to think about sample size. What I've given you now is a very simple example of it, right? But the different kinds of outcomes. Sometimes there are dichotomous outcomes, like yes or no, versus a continuous outcome, which is amount of blood pressure change. Sometimes you look at survival time, time to event, etc. We've looked at so far a experimental design, but if we're doing a case control or a survey design, then the formula will be different. And sometimes you need to consider things like cost. How many can I afford to recruit? If I can't afford to recruit what I computed, then I have to modify some things. Usually I modify the effect size. I say, well, I can't afford to to recruit 16 people, so I'm going to change the effect size to something larger. Okay, summary. Sample size increases with increasing variance. It decreases with the effect size needed to detect. It decreases with type 1 and decreases with type 2 error. That is all for the first lecture. Yay, moving on. Okay. All right, new topic entirely, kind of related tangentially. The last topic of the year. How exciting is that? You're not supposed to be so happy, Aparna. Looks sad. Yeah, fine. Okay, and it's a little bit mathy, but not too badly. This is matched studies. Okay, we touched on a little bit of this in second-year statistics. We looked like things like t-tests, comparing twins to each other, or husbands and wives, or things like that. Okay, so let's talk a bit about case control studies. If you remember, case control studies begin with ascertaining the outcome and looking backwards in time to see what the exposure status was, right? So you find some people with lung cancer, some people without lung cancer, and you look back to see who smoked. And we mentioned briefly that it matters how you choose the controls. It matters how you choose the people who don't smoke, because people who don't smoke, that's a pretty big population. Right? Do we care about if they didn't smoke and they were female, or they're in the same hospital wing? And I showed you that example of the spurious association between coffee drinking and pancreatic cancer based upon inappropriate selection of controls. So how you choose a control is very important. But case control studies are not very expensive, because I don't have to wait a long time to collect people. I can go right to the clinic, get some disease people, get some controls, look at the medical records, bing, bang, done. Right? So the quicker to conduct, it's pretty good at getting causal relationships, because we kind of know what came first, the exposure or the disease, et cetera, et cetera, et cetera. And I mentioned that it's really useful when the disease is rare. So we know all those wonderful things about case control studies. If you've forgotten, this is what it looks like. It's a population. We find some people with a disease, who are always called cases, people without the disease, and we look at the proportions of exposure in both groups. Look at these data now. This is not an uncommon way of depicting case-controlled data. Get used to it. This is from a textbook, Gordon's textbook. So here we have cases, the numbers that were exposed, the numbers that were not exposed. This is how an outbreak investigator would write down data. So let's say we're going to a picnic, because you heard there's a diarrhea outbreak. That's what we do. Go to picnics, look for diarrhea. Sexy, right? So people with cases, these are the people with diarrhea. Cases are always diseased. And the controls are the ones who didn't have diarrhea. And we say, well, Bob, he was a kid who got diarrhea, but he didn't eat the chicken salad, right? Oh, he did eat chicken salad, right? And Susie ate the chicken salad, but Frank, he didn't eat it, and so forth, right? Now, how will we fill in our contingency table? Well, how many of the cases were exposed? 1, 2, 3, 4, 5, 6. How many of the controls were exposed? 1, 2, 3, 3. How many of the cases were not exposed? 1, 2, 3, 4, 4, and so forth, right? That's how you fill in that table. That should be pretty straightforward. We can compute things like odds ratios. Remember, we compute an odds ratio here rather than a relative risk. Why? Why is an odds ratio appropriate for a case control design and not a relative risk? Yes, sir? Exactly right. Exactly right. Relative risk depends on a ratio of incidence rates. That has no meaning here, so we compute odds ratios instead. So you remember how that's done. So this gives us an odds ratio of 3.5. Fantastic. Okay. So how do we reduce the chances of poor choices of controls? We do it through matching. Matching what? Like I said, well, I want to reduce confounding due to various things. Well, I'll make sure that we got equal numbers of men in both groups, or people in the same hospital wing, that kind of thing, to control for the things like the foods that they ate, the care that they got, their sex, their genetic dispositions. I can control for anything if I match. But matching can be problematic. So very often we match in terms of age, sex, race, anything demographic. You may remember these are also the primary confounders. Classic confounders are age, sex, smoking status, and SES, socioeconomic status. those are the things we typically match for to control for confounding. So again, matching is a great way to control for confounding. It's like stratifying within study design. Okay, we can either do it by frequency matching or individual matching. Frequency is also called group matching. Individual matching is also called paired matching. What does that mean? Well, frequency or group matching is when we make sure that there are equal proportions of the thing that we care about in both groups. So we can have 25% of the cases are black. That means 25% of the controls have to be black as well, right? Or female or whatever, right? That's not perfect, but it kind of helps control for it all. Individual matching, we make sure that for every one person, there's another matching person with the same characteristics other than the thing that we came for, which is like the disease state or the exposure state, right? So the problem with matching, though, is some practical problems. Sometimes we can't find things to match for. Also, if I care about 1,000 different factors that might be confounders, I got to find 1,000 different matching properties. In other words, I'm looking at twins, one twin who got cancer and one twin who didn't get cancer. That's the ideal match. The other is conceptual. So once I've matched for something, I remove the ability to detect the effect of that thing. So think about it. If I've made sure that for every smoker, there's a smoker over here, and for every non-smoker, there's a non-smoker over there, then I don't know now if smoking was a factor that played a role in the outcome that I'm looking at. I've taken it out of the analysis equation. Usually that's a good thing. Usually I'm trying to dispose of extraneous factors, but sometimes I want to detect it. So the kinds of analysis we're doing, it doesn't come into play because we're doing very simple one-factor analysis. But if we're doing multivariate analyses, looking at a variety of factors and how they predict certain outcomes, this can be important. As a result, we have the problem of unplanned matching. So if I chose some controls at random, by some chance, it's possible that I got exactly the same number of women, exactly the same number of a certain ethnicity, exactly the same number of smokers, and so forth. If that happens, then maybe I will not detect the effect of those things, and I wanted to. So it can be dangerous. So we think about it in some depth before we match. Okay, here there are different ways of selecting controls. There are multiple controls and single controls. So multiple controls, single controls are for every person there's another person. Multiple controls come in two categories: multiple controls of the same type or multiple controls of different type. What does that mean? Well, with multiple controls of the same type, I can say, let's say I'm testing again for lung cancer and smoking. Case control analysis. I got my lung cancer patients. I only found 15 of them in the clinic. Fantastic. But I really want to up my sample size. So instead of getting 15 controls, I'm going to get 45 controls. I'm getting a lot of controls, multiple controls, but they're all the same. They're all non-cancerous people. Okay? So that's the first type here. I'm just upping a large number of controls to make sure my sample size is buttressed. With different types, well, that gets a little more complicated. So let's go through them here. First, let's talk about the same type. So for a rare disease, like here we have cancer, connective tissue disorders, the number of cases are limited. It's hard to find cases, so my sample size are going to be small. So I'm going to increase my sample size with controls, and that will solve most of my problems. Right? Oftentimes, you have multi-center collaborations to allow this to happen. So practically, getting numbers of people can be problematic. But the different types, this is where things get fun. So if I have different control groups, now I can make fun comparisons. So here I've got my cancer group. Maybe I've got a bunch of different control groups. I have a control group that doesn't have cancer but does have heart disease. I've got a control group that doesn't have cancer or heart disease. Here I've got a control group with no cancer, no heart disease, but they got like a third arm or something like that, right? So I can compare this one to that one, this one to that one, this one to that one. That happens all the time, especially if it's expensive to find my original disease group in the first place. Let's not waste them. Let's compare them to a bunch of different groups. So that's multiple controls of different types. Okay, so it's useful for comparing a variety of interesting exposures. like different neighborhoods, or comparing a hospital population to a community population to an experimental population. Okay, as an example here, let me see here. Here's an example. Okay, so the control, here we have, we're looking at cancer and its relationship with radiation exposure. So we've got two control groups here. We've got the case group, which is kids with brain tumors. This is a fun topic, right? It's children with brain tumors. That's our case group. Two control groups. We have kids with no brain tumors, but with other kinds of cancer. And the other control group is kids with no cancer whatsoever. Okay, so here are the groups. There are cases, kids with brain tumors, kids without cancer, and kids with cancer but not brain tumors. What do we do with this? Well, these are our two possibilities. We can have either end up with a lot of radiation exposure in both cancer groups. That tells us that radiation is associated with cancer regardless of what kind of cancer. Or we can have a situation where we have radiation just in the brain tumor group. It says, oh, radiation is associated with brain tumors but not other kinds of cancers. So this conclusion here allows us to say there's something specific about this exposure of radiation to this outcome. This conclusion will allow us to say there is something unspecific about radiation and its exposure to association with cancer, but there is an association. And you can imagine we can throw in other kinds of control groups if you want. Kids with no brain cancer, no brain tumor, no cancer, but with genetic abnormalities, whatever it might be. So your imagination is free to run fine. Okay, so why do we match again? Remind me, what's the purpose of matching? To control for what? Whisper, 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 whisper. This is why she left early. She knew she didn't know the answers. I pick on her. Why do we control? What do we control for? We match. Yes? Confounders, exactly. Yay! Fantastic. Okay. So this is the same data we had before with the picnic. We've got some people with diarrhea, some who don't have diarrhea, those who ate the egg salad, those didn't, and we said the odds ratio is 3.5. Fantastic. Now we're going to look at how to compute an odds ratio if the study were matched instead. So to do so, we have to think about concordant pairs versus discordant pairs. And by the way, the example I'm going to use is just about individual matching, not group matching. So I won't show you how to do the math for that. It's just for individual matching. Concordant means both the case and the controls were exposed, and discordant, or neither one were exposed. With discordant pairs, one of them was and one of them wasn't. So concordant means sameness, discordant means not sameness. Okay, so let's say that our data look like this. When we're looking at matched odds ratios, we're looking at pairs, not individuals. Pairs, not individuals. So the first pair of people, one was exposed, this is the cases, and his matching control was also exposed. The second pair, the case was not exposed, but the control was. The third pair, the case was not exposed, and the control was not exposed. So again, the case is the person with the diarrhea, and the control is the person without the diarrhea. Let's say we're controlling for lactose intolerance here. Okay, so pair number one, both of them have lactose intolerance, right? And one of them got diarrhea, one of them didn't, but they were both exposed to getting the egg salad. This one here, number three, let's say both of them don't have lactose intolerance. This guy who got the diarrhea did not eat the egg salad sandwich, and this one who didn't get the diarrhea did get the egg salad sandwich, and so forth. That's how you disentangle these data. Okay, if we assume this was not a matched study, can you go from this to an unmatched contingency table? Yes, you can. It takes a little bit of logical work, but you can, and some asshole professor may ask you to do that. So if I said this is the nature of your paired data, you can convert this to a regular contingency table. For example, how many people were exposed and got the disease? Well, who got the disease? These guys. 1, 2 of them were exposed. How many people were not exposed but got the disease? These guys here. These 2 were. 2. How many people were exposed but did not get the disease? Among the controls, 1, 2, 3. 3 were. So I can go from here to there quite easily. I can't go from here to there. If I gave you this information and asked you to make the paired table, you could not do so. But I can go from the pair table to the unpaired contingency table. And here the odds ratio is just this times that divided by that times that, which is 0.33. Okay, fine. Now, let's organize the data preserving the matchedness. Right? So with matchedness, we care about the paired status. Remember, we care about concordant pairs and discordant pairs. So it looks like this. The table you want to fill in looks like this. We have controls up here, cases over here, exposed, not exposed, exposed, not exposed. Take a second, wrap your brain around what this looks like. The data that goes in here will be the number of pairs, not individuals, the number of pairs. So how many pairs were both exposed among cases and controls? This one, just one, looks like, right? How many pairs had cases exposed but controls not exposed? Just one, right? How many pairs had cases not exposed but controls exposed? Cases not, looks like two pairs were. So you fill these in, and the data looks like that. Okay. So in no pairs were the cases not exposed but the controls exposed. And there's no example of that here. So again, this is pairs, a number of pairs of people. Fantastic. What do we do with this? Well, if you think about these labels for these cells, A and D are the concordant pairs, meaning both of them are exposed and or both of them are not exposed. The discordant pairs are the ones where there's a difference between them. It's the discordant pairs we care about. Those are concordant, these are discordant. Okay? The ratio, odds ratio for discordant pairs is B over C. That's what we care about here. So a matched odds ratio is B over C, 1 over 2, or 0.5. What was it before we matched them? It was 0.33. With the matching, it goes up to 0.5. That shows us that confounding characteristic, lactose intolerance, was hiding a fair chunk of the odds ratio, went from 0.33 to 0.5. We took out the influence of lactose intolerance, and the odds ratio changed. It didn't change direction, unfortunately. It didn't go from like 0.33 to 1.7, which would have been exciting, but it changed magnitude. Okay, another example. Here is an outbreak of meningitis in Germany, and we're asking ourselves, was swimming in the pond labeled A risk factor? Right, so it's a case control study, and here is what it looks like. This is the matched pair data already filled in for you. We have 194 pairs of people who are concordant in exposure and 29 who are concordant in non-exposure. But these are the ones we care about, the discordant pairs. The odds ratio here is going to be 46 over 6 or almost 8. That's pretty high. That tells us that there's a strong association between swimming in this pond and getting meningitis. And what were you controlled for? I don't know what they control for. Let's say they control for family history of meningitis. I don't know. Okay, what else can we do with these data? We're going to do a little bit of chi-square. You remember this from your second year stats. Again, this is the very last thing we're ever going to do in epidemiology this year. How exciting. So sad. I kind of feel bad about skipping the decision analysis now. So remember back when we did odds ratios and relative risks, and we said that a strong relative risk would be like 1.2 or 1.5 or 2. Things of that magnitude tend to set off public health alarm bells. But when you see an odds ratio or relative risk in a paper that I'm sure you've all read now that you've done your poster assignments, you probably saw a p-value associated with that relative risk or odds ratio. So when we compute these things, there's always a p-value. What's a p-value? A p-value is, well, who wants to say what a p-value is? Do you remember? What's a p-value? Yes, sir. Well, yes, that's correct. But can you interpret it for me?
Generally, if it's less than alpha, so p is less than 0.05, then if that's what you chose as your alpha, then it is.
Yes, that's how you use it. That's correct. But can you tell me philosophically what a p-value is? It's a tough question. It's something that I encourage students to wrap their brains around. What it is, technically, is if the null hypothesis were true, what is the probability of finding your result? Okay, so if you cast your mind back to the blood pressure example, and let's say the p-value computed was 0.03 or something, what you're saying there is if the blood pressure medication did not work, there is only a 3% chance that you would have seen the results that you got. And the question you ask yourself is that unusual, yes or no? Is that extreme? Is it so unusual that it's extraordinary? And if it is extraordinary, then we can say, well, maybe the null hypothesis isn't true. Maybe we can reject the null hypothesis. So is 0.03 extraordinary? Well, it is if we say it's less than 0.05, and that's what your cutoff is. So we say, well, it's extraordinary enough. So the p-value is the probability of you seeing the results that you saw if the null hypothesis were true. So to catch up to what we're talking about here, when you look at these papers, you see there's a p-value associated with the relative risk. But we didn't interpret that. We've been looking at solely the size of the relative risk, the 1.7, the 2. Whatever it might be. So one of the ways to compute a p-value that is sort of associated with the relative risk or odds ratio is to use the chi-square non-parametric statistical test. These days we use different kinds of tests, but this is one way to do so. And we're going to go through it manually, just for fun. Okay, it's a non-parametric test. If you remember your statistics, a non-parametric test is one that does not rely upon a distribution in the general population. So it will tell us the degree of confidence that we have in whether or not two categorical variables are related. With the relative risk, we have like an exposure, an outcome. Those are categorical variables. So it allows us to compute a p-value. So there are lots of chi-squares. Here's a few of them: Pearson's, Yates, Mendel, Hansel, etc. We're going to be computing Pearson's chi-square. A couple things to keep in mind. It doesn't work if any number in the cell is less than 5. If it's less than 5, we use something called Fisher's exact test or something like that. We'll not be doing that in class. Okay? The examples I give you hopefully will all be 5 or more in the cell sizes. I believe the example we're doing here doesn't, which means I screwed up a bit, but whatever. So this is the formula for a chi-square. It's the sum of the observed data minus the expected data squared over the expected data. What does all that mean? And we need to compute something called the degrees of freedom as well. You're probably having nightmares about stats class now. Degrees of freedom, what's that? It doesn't matter. If you must know, it's some kind of proxy measurement for the number of things in your sample. That's all it kind of is. It's like n, but it isn't. So this is how the data is displayed in a chi-square table. So this is your outcome, or that's your exposure, or whatever. The data goes in here. These are the marginals. We've done this a billion times. Right? The chi-square is just this formula here. So you can do it this way, or you can do it the hard way, which is this. But it's easier to memorize that formula, or write it down in your cheat sheet. Okay? The degrees of freedom is going to be the number of rows minus 1 multiplied by the number of columns minus 1. In this case, there are 2 rows and 2 columns. So 1 times 1 equals 1, 1 degree of freedom. So let's say this is a data looking at the survival or the experience of certain animals that were experimented on and whether or not they are dead or alive. So our cases are animals that died, our controls animals are alive, and we see whether or not they experience these treatments. And this will be a typical way to use this analysis in a laboratory context. Did our mice survive? Do they have the drug or did not have the drug? These are our data. We plug in the data into our formula, and we compute a chi-square of 3.4. What do I do with that? Well, I compute my degrees of freedom, and I look up in the back of a textbook on a chi-square table to see if that's significant. Oh, but sir, there isn't a chi-square table in a textbook. I know there isn't, I know. But I give you one over here. And on an exam, of course, I'll give you this to put this in your cheat sheet. Okay? So the way you'd read this is we computed here our chi-square is 3.4. Our degrees of freedom is 1. Degrees of freedom is 1 here. Where is 3.4 rather? It's between these two over here. So our p-value is going to be between 0.05 and 0.1. Okay. If my alpha is 0.05, is this association significant? Can I reject the null if I say my p-value is between these two numbers? Is it significant? Yes, ma'am? I would not reject the null because clearly, if this is my cutoff, I'm above my cutoff. We're saying that my observation is not extraordinary enough for me to reject the null. In real life, nobody uses these tables. In real life, nobody uses chi-square. We kind of stick to it because we can do it by hand, but we have computers now. But we do this to, yes. Yes, I will give you the table. Yes. Okay, so after doing all that, now we know that there is no statistical association between the treatment and whether the animals lived or died. At least not at this cutoff level. Okay, so what relevance does this have to your odds ratio or relative risk? If you were to compute a chi-square for your odds ratio or relative risk data, what it's testing is a certain null hypothesis. The null hypothesis says nothing's going on, right? For nothing to be going on for an odds ratio or relative risk, it has to be equal to 1. So it's really testing, is the relative risk or odds ratio statistically different from 1? That's all it's saying. Right? So a p-value of 0.1 means, if the null hypothesis is true, if the relative risk is actually 1, nothing's happening, there's a 10% chance of getting the data that I got, which is a pretty high number. So in fact, the null is probably true. Relative risk is probably 1. And if we fail to reject the null, it means the relative risk is probably 1. There is no association. It's a lot of work to do. Okay? So as I said, in a cohort study, the chi-square tests whether or not the relative risk is 1. In a case control, it tests whether the odds ratio is 1. We do not use it for matched studies. We use something called McNemar's test, which you won't do in this class, which I do at my second year stats class. Maybe you did it in yours, I'm not sure. But keep that in mind. We don't use it for matched studies, just for these two. So I may ask you in an exam, compute the relative risk for this, and tell me, is it significant using the chi-square method? So here is our picnic data. Again, let's unmatch it. Let's unmatch all this. Right? Remember how to do that? We look at the number in which there's exposed cases. Let me see, 1, 2, right? Et cetera, and we get our odds ratio here. So we're going to compute the chi-square for these ones. We do the math, and plug it in. Now, you can also go online and do it that way if you want, but I want you to do it the hard way. And here's some homework for you to try. We've got, where's my homework here? There we go. Right, so I want you to try some matching studies over here. I want you to use these data and try to match them. And I want you to answer these questions. Done. Fun. Last actual new stuff of the year. Exhausting, right? But we'll see you on, probably see you on Thursday in office hours, but definitely on Friday. Look out on Tuesday when I upload the schedule for your presentations. Any questions? Out with a whimper.